Hi, my name is Alma Cooper, and this is my midterm proof. So, the first step that we are going to make along our proof journey is we're going to map out our steps through a flowchart. So, the first step is to identify our no in our show. And so, one of our no's is the definition of convergence. So, what does it mean for a sequence to be convergent? That's what we want to put out on the table and begin to use as a puzzle piece for our proof. The second no is the triangle inequality. So we're going to talk about what the triangle inequality is and then how we can use that again as another puzzle piece in our proof. Throughout using the definition of convergence, we want to know what the use of epsilon does for our proof solving process. So what role does it play in our proof and how can we use it to our advantage? And then finally, what is the Cauchy sequence and how are we going to get there through our proof work? So our proof statement is that if a sequence is a convergent sequence of real numbers, then that sequence is a Cauchy sequence. So the definition of convergence. The definition of convergence is a sequence in R that is said to converge to X belonging to the reals, or X is said to be a limit of X sub n, that sequence. If for every epsilon greater than 0 there exists a natural number k, such that for all n's that are greater than or equal to k, the terms x sub n satisfy the absolute value of x sub n minus x is less than epsilon. So the definition of convergence plays a big role in this because it is the first part of our proof. It's the first puzzle piece that we have to mold towards proving our show. And so by using the definition of convergence, we will be able to mold our sequence coupled with the triangle inequality in such a way that allows us to achieve the statement that x sub n minus x sub m, the absolute value of that, is less than epsilon. So the triangle inequality, I've been mentioning it prior to this definition, but really what it is, it's a way for us to arithmetically show that x sub n minus x sub m is less than epsilon. And so you will see how in Bartle's proof, he uses x sub n minus x sub m with epsilon being epsilon over 2, when in reality you can use regular epsilon. But if using regular epsilon, what you'll end up with is 2 epsilon at the very end. And so he uses epsilon over 2. I use regular epsilon, but we're both sharing the same thing, where he just uses it to make his proof look nice at the end, with the finishing touch being that you neatly get epsilon, but it's the exact same thing. We'll just use the triangle inequality to add 0, and then we'll see how it works out in the end, where we end up with 2 epsilon, which ultimately still shows that x sub n minus x sub m, the absolute value of that, is less than epsilon. Again, I've been saying epsilon a lot, but really what it's saying is that at the end of our proof, given any epsilon greater than 0, we'll end up with x sub n minus x sub m is less than epsilon. So the Cauchy sequence. To have a Cauchy sequence, you're saying that a sequence of real numbers is said to be a Cauchy sequence if for every epsilon greater than 0, there exists a natural number h, such that for all natural numbers n, comma m, that are greater than or equal to that h, the terms x sub n and x sub m satisfy the statement absolute value of x sub n minus x sub m is less than epsilon. And so we'll show that using our two no's, the definition of convergence and the triangle inequality, we will be able to achieve x sub n minus x sub m. The absolute value of that is less than epsilon. So the first step is we'll apply the definition of convergence by stating that we have a sequence that is not a non-empty set and it's in R. So a sequence of real numbers. And we'll let x be the limit of x sub n, our sequence. Then, given a random epsilon greater than 0, there's a natural number k, such that for all n's greater than or equal to k, the terms of our sequence satisfy x sub n minus x, the absolute value of that, is less than epsilon. And so this is nothing new that we haven't seen before. This simply is just restating the definition of convergence and how we will use it to our advantage. I want to point out one thing. The definition of convergence allows us to get x sub n minus x being less than epsilon. What we want is x sub n minus x sub m to be less than epsilon. And to be able to do that, we'll use the triangle inequality, and we'll show that by adding 0, we will end up with x sub n minus x sub m being less than epsilon. And we'll also show the close similarity between k and the value h, both being natural numbers, how they are similar. The only difference is that x sub n minus x sub m is satisfied by the letter h, and in this case, with the definition of convergence, we have a k. And so we'll see that later on in the proof. So now we'll apply the triangle inequality in order to arithmetically show the Cauchy sequence is achieved. Just a reminder, we've seen it before, but just to give us a hint, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b is the triangle inequality. And so all we're doing is we're adding 0, which is the subtraction of x and the addition of x, and then continuing with our concept of x sub n minus x sub n, m being less than epsilon. And so this is where we incorporate that x sub m. I'll have the absolute value of x sub n minus x sub m equaling the absolute value of x sub n minus x plus x minus x sub m being less than or equal to the absolute value of x sub n minus x plus the absolute value of x sub m minus x being less than epsilon plus epsilon equaling 2 epsilon. And again, like I said earlier, 2 epsilon still means that we have x sub n minus x sub m being less than epsilon. It just so happens that we end up with 2 epsilon, while Bartle's proof using epsilon over 2 for his original epsilon ends up with the final value being epsilon. And again, we've shown that this value is less than epsilon. And again, I mentioned it earlier, but I'll point it out again. We can really see it here. Similar to the existence of a unique natural number k, there too exists a natural number h, such that for all natural numbers, not only is it n, in the first case we saw that n was greater than or equal to rk, but here with h, it's set up such that n and m are greater than or equal to h. And so also we'll know that k and h are unique in the fact that they are unique to that epsilon that we've chosen. And so the terms x sub n and x sub m satisfy x sub n minus x sub m, which are less than epsilon. And so now we will use it in a formal example. So we'll let our sequence be a non-empty set in R, and we'll use the sequence 1 over n. And so given a random epsilon greater than 0, there exists a natural number h, such that for all natural numbers, n and m being greater than or equal to h, the terms x sub n and x sub m satisfy the absolute value of x sub n minus x sub m is less than epsilon. This sounds familiar, right? So just another reminder, we'll use the triangle inequality. And what we're doing with the triangle inequality is we're basically adding an x and we're subtracting an x to get the addition of 0. And so because we have, added nothing to our equation, we have shown that, maintaining the spirit of x sub n minus x sub m, we still maintain the idea that in and of itself is less than epsilon. And again, we end up with 2 epsilon, which is still the same as saying less than epsilon because we just used regular old epsilon instead of epsilon over 2 like Bartle. So we'll have the absolute value of 1 over n minus 1 over m equals the absolute value of 1 over n minus x plus x minus 1 over m less than or equal to the absolute value of 1 over n minus x plus the absolute value of 1 over m minus x being less than epsilon plus epsilon, which equals 2 epsilon. So that concludes our proof, and thank you for your time.